Hello, and welcome to Mr. Ambrose's video on series. Um, Hope you are enjoying the snow day and remaining safe. What I'd like to do in this video is to review with you guys first, or pick up at least where we left off in class yesterday with our integral test. And I actually just want to go through the two examples that we looked at before I give you what the integral test actually is. So the first series that we looked at was a harmonic series. That's the series with general term of 1 over n. The first few terms of the series are 1, a half, a third, and a fourth. And what we did was we compared or looked at the function with the same type of general term as our series. We looked at the function y equals 1 over x. And I constructed these rectangles, at least these four rectangles here, such that when we calculated the areas of these rectangles, we see that they equated to the terms of our series. And so I could technically continue to do this after x equals a 5 out forever until infinity. And if we did that, if we compared the terms of our harmonic series with the area of those rectangles, right, they would be exactly the same. Now, understanding the geometric applications of our integrals, being that it captures our area underneath the curve, when we compare the area of those rectangles to the improper integral of 1 over x from 1 to infinity, it's clear to see that the area of these rectangles should be greater than the value of this improper integral. And then when we value this improper integral, right, we got a value of infinity. So because the evaluation of this improper integral gives us infinity, we would say that the improper integral diverges. And since the improper integral diverges, that means that the harmonic series itself must also diverge. At the end of the class yesterday, then we looked at another series with general term of 1 over n squared. The first few terms of that series are 1 1/4, 1/9, and 1/16. I then considered the curve with the equation f of x equals to 1 over x squared. And then I proceeded to draw these other rectangles in here. Now, actually, though, I happen to have drawn those rectangles beneath the curve. And the areas of these rectangles are 1/4, 1/9, 1/16, and 1/25. As with the problem with the harmonic series, we could continue drawing out rectangles all the way out to the right, out to infinity. And now the only issue here is that technically, if I continue to do that, I would pretty much capture all the terms of this particular series, but we would be excluding the first term of 1. So what we could do is we could say that, all right, here we have this series with general term of 1 over n squared that will equal the area of the rectangles starting at x equals 1 all the way out to the right, but we would have to then add to that the value of 1, the value of the first term of our series. And now that we have this set up, if we compare this to the improper integral with function of 1 over x squared, evaluated from 1 to infinity, and then add 1 to that result, the area of the rectangles plus 1 should be less than the value of this improper integral plus 1. And so when we evaluate the improper integral, that itself will give us a value of 1, and if we add 1 to that, we get a value of 2. So since the improper integral here is conversion, and the series itself must be less than the value of this improper integral plus 1, that means that our series must also converge. And so you see here two different problems where we basically kind of analyze improper integrals with functions that had the same variable expression as the general term of our series, and basically whatever the improper integral did, converge or diverge, so goes our series. And that basically is our integral test. There are three conditions that have to be met, and if those three conditions are met, then we essentially evaluate our improper integral. So the conditions are that, number one, you have to have a function that behaves exactly like the general term of your series for n values starting at some arbitrary number, usually 1, out into infinity. And I should say the smiley face does have to be some positive integer. Second, our series itself has to have all positive terms. There can be absolutely no negative terms in the series. If there was, then we would not be allowed to apply the integral test. Then the third condition is that our function f, that is analogous to our general term of our series, must be a function that is both decreasing and continuous on the interval from infinity, smiley face to infinity. If all three of these conditions are met, then basically we can apply our integral test. And the integral test is basically going to involve initially evaluating the improper integral of the relevant function from usually 1 up to infinity. And the basic gist is that whatever the improper integral does, so does our series. So if our original series converges, if our improper integral converges, then our series also converges. But if our improper integral diverges, then our series will also diverge. Now this is an explanation of the integral test. If you would like to see a more formal proof of how the integral test actually works, I'll be more than happy to show you in either extra help or in a free moment that we might have in class. So let's now apply this integral test. Here are two problems. We want to determine the convergence of each of the series, and we're going to do so by applying the integral test. So why don't you guys perhaps pause the video, try to apply the integral test to each of these series, and then you can unpause it and I'll show you the solution to each of these problems. Good luck. Okay, so here is a solution to the first series with general term of 1 over n cubed. The related function that will behave exactly like 1 over n to the n third power is this 1 over x to the third power. This 1 over x to the third power is a function that will be decreasing and continuous, starting at 1 off to infinity. So, and all the terms of this series, I should also say, are all going to be positive. So we can apply our integral test. So we take 1 over x to the third power, we will set up this improper integral from 1 to infinity, and then we just have to evaluate this. So we can substitute t in for infinity, we can put our limit out in front of this improper integral, and then we just have to find or evaluate that improper integral. The antiderivative of 1 over x cubed is negative 1 over 2x squared. So we plug t first into the antiderivative, and then we plug 1 second into the antiderivative, and then we have to evaluate this overall limit. And as t approaches infinity, this first fraction is going to go to 0, and we are just left with 1/2. So since we get a finite value, that means our improper integral converges, and since the improper integral converges, then our series also, we say, will converge. It converges. Sorry. The second problem with series of general term 1 over square root of n, hopefully it's apparent that all the terms of this series will be positive. The analogous function that will behave like 1 over square root of n would be this 1 over square root of x. And this function 1 over square root of x will be decreasing and continuous, starting at x equals 1 out until infinity. So we can set up this improper integral from 1 to infinity of 1 over square root of x. We substitute in t for infinity, we introduce our limit notation, and then we have to find an antiderivative for the 1 over square root of x. And the antiderivative of 1 over square root of x would be 2x to the 1/2. And then we plug t in first into the antiderivative, we plug in 1 second into our antiderivative, and then we evaluate this expression as t goes off to infinity. But unfortunately here, that will mean that the value of this limit will be infinity. Since we get infinity as an answer, that means our improper integral diverges, and since our improper integral diverges, so goes our series. So hopefully now you have a better understanding of the integral test and how it works. You could try perhaps some problems from your textbook on page 545, question numbers 7a and number 9. You can apply the integral test there to perhaps try and determine the convergence of those two series. And based upon the way the weather is right now, it looks like we will have school tomorrow, so we'll go over these problems first thing in class, and then after that we'll examine pi and how we can determine it and maybe actually have some pi. All right, enjoy the rest of your day. Take care.